Just letting everybody come on through. Since we had to restart. Did everybody catch that? Did you guys see how that happened over here? What happened to the 1 squared? 1 squared is 1 times 1, which is 1, so it just turned into a 1. Right here. And 1 times 2 is just 2. And there was a negative there, so we put the negative there. Does that answer your question, Tyler? Yeah, but I feel like a 1 is missing. Let me take a look here. So we got, this became a 1 cubed, which is 1 times 1 times 1, which is 1. That comes here. This becomes a minus 2 times 1 squared. So that's 1 squared, which is 1, times the 2, which was negative, which is negative. Then there's this 1 over here. That comes down here. Then there's this negative 5. That comes down there. So no, there isn't a 1 missing. Very good. Yeah, there's a lot of 1s floating around, so it's really hard to get confused. That's why now we're going to evaluate it for f of 2. No, actually, let's spice it up. Let's spice it up. We'll do f of negative 2. How about that? Agreed. Okay. Agreed that we should spice it up. So we get our original function here defined in the x's, and we'll carve out the x's here. Put a cubed here, minus a 2. I'm going to carve out this part here, plus right here. I'm going to carve this part out, and I'm going to put this minus 5 over here. And let's delete this stuff so it doesn't interfere visually with what we got. Okay, so now once we've carved out all of the regions that contain x's, we fill it in with what's in here, that negative 1. Or negative 2, I mean. Okay. So now we compute. What does this equal? Negative 2 cubed is a negative 2 times a negative 2 times a negative 2. So this becomes a negative 8. Minus a negative times a negative. Does it remain negative? Because negative 2 squared is positive 4. Okay? Then positive 4 times negative 2 ends up becoming negative 8. All right? So next, now we add it to a negative 2. So it's basically like subtracting a negative 2. And finally, we have to subtract that negative 5. Okay. So this becomes negative 16. That becomes negative 21. That becomes negative 23. So f of negative 2 is negative 23. What is f of This is not spicing it up. This is making it easy. We'll carve out all the x's. Okay. Then inside the carvings, we'll place in that 0, because that's what we're evaluating this function at. Okay. And then we compute. 0 cubed is 0. Minus 2 times a 0, which is a 0. Plus a 0. Minus a 5. Clearly, this is negative 5. That's the only non-zero number in the array. Does that make sense? Cool, cool. Let's do a different function. Let's do f of x is equal to 1 over the square root of x squared minus x. Let's evaluate the function at f of 3. What is f of 3? Well, I'm going to rewrite our function, carve out all the x's. Okay. Once I've done that, now I'm going to put in that 3 in there. You look at that, okay? That's what we get. So this equals 9 minus 3. That equals 6. Square root of 6. Okay. The square root of 6 doesn't break down to anything more simple than that. Okay. Of course, we can rationalize the denominator if you'd like, multiplying top and bottom by root 6. This is not a necessary step, but sometimes a step that is required of you for your inputs. So what we would get is this. This could be our final answer, but also we could have equivalently said that it was just 1 over square root of 6. These are both equivalent. They're both equivalent. So what would be the f of 2? Oh, actually, let's do f of negative 4. That would be 1 over the square root of, let's carve out the pieces. Okay. Notice that this is equivalent to 1 over the square root of negative 4 squared minus a negative 4. Okay. I'm going to move the calculation down here because we're running out of room. Or I could just keep going here, actually, since I erased everything. This is the same thing as 1 over the square root of negative 4 is 4. Negative 4 times 4. So negative 4 times negative 4 is a positive 16, right? And this is a negative 4. Ha! And we know for sure that that is a positive 4. From our discussion earlier, we've shown that y and negative times a negative is a positive. Because negative 4 is the same thing as negative 1 times the negative 4. Notice that this reduces to 1 over the square root of 20. Okay, if you would like, you can rationalize the denominator and say that that's root 20 divided by 20. But these are both equivalent answers. I will warn you, sometimes computers don't know that this is the equivalent of that. So if a problem asks you to rationalize the denominator, this is what it's looking for. And we went from here to here. Don't forget, we went from there to there by saying 1 over square root of 20. Multiply top and bottom by fancy number 1, square root of 20 over square root of 20. Notice that this is what results in square root of 20 divided by the number 20. Make sense? Good. All right. Well, now it's just getting trivially boring, guys. Why don't we kick it up a notch in our function evaluation game? Because, you know, us mathematicians, we get bored really quickly if we don't have intellectual stimulation. So let's just turn it up and make it a little bit spicier. Let's say we have f of x is defined as x divided by x squared minus x plus 3. Evaluate f of a plus b. You were not bored? Oh, well. Now you're definitely not going to be bored. Okay? So, let's do our whole carving thing out. And you know, it's especially appropriate during this time of the year. People are carving turkeys, carving pumpkins, what have you. So what I did was I carved out the x's. And I'm priming them to insert what is inside that parentheses by the f, which is namely that a plus b. So I put that there for all of them. So what does this reduce to? You can't just stop here, because I don't want you to just evaluate f of a plus b. I want you to evaluate and simplify. So we got to FOIL or distribute here, if you will. So the top just stays a plus b. The bottom gets a lot more interesting. Notice that a plus b quantity squared is the same thing as, you know, a plus b times itself. Right? Notice that that equals a squared plus 2ab plus b squared. So that is what's going to go here. A squared plus 2ab plus b squared. And here's the part where I see a lot of students mess up. And this minus sign in front of a parentheses of two things added or subtracted to each other. That minus sign cannot just go on the A. It must distribute to the A and to the B. So that's why we get this minus A and minus B. A lot of the time students will put the minus on the A, but neglect to put it on the B. And that is wrong. It has to distribute to both. Why? Oh, I'm glad that you asked that. Although all of you are on mute, I heard someone ask it. So notice if this is A, okay, and this is B, okay, A plus B is probably somewhere over here. All right. So the negative of A plus B, that's what this is right here, is going to have to be over here. For you to just say that the negative of A plus B is just negative A plus a positive B would mean that it could possibly only just be right here. See, this is not the same location as that. Truly distributing a negative to this parentheses term, I have to distribute it both to the A and to the B to get it to go to the right location. Isn't math much better with pictures? Yes, absolutely. Everything is better with pictures. Of course. But you see, mathematicians create these pictures for themselves. And mathematicians see these pictures in their heads. And the teachers who taught you this stuff did not see these pictures in their heads. And so they did not teach you this stuff this way, which is a shame because it's very, very, very intuitive if you just draw a picture. Okay? So we distributed the negative, and so we have to, at the end, add a 3 plus 3. Now, notice that there's nothing to regroup. There's no terms that can cancel. We actually have it in the most expanded form. So we're actually done. We're actually done. Okay. Does that make sense? Any questions so far? Makes much more sense now, thanks. Very good. All right. Let's do one more interesting example where we talk about functions. You guys remember the vertical line test? Who here remembers the vertical line test? No, sir. You don't remember the vertical line test? Oh, no questions. You remember the vertical line test, right? What was the vertical line test about? You just put a vertical line through a function, and something about that is special, right? You find the location of the function. Kind of, not really. The vertical line test, and let me keep this much more neat looking. The vertical line test is a test to see whether what you have is a function or not. To see how many functions go through the line. It does relate to testing whether something's a function or not. So here's a vertical line test. It says, given some function on your graph, we will do the vertical line test. That means any vertical line I draw, it must intercept the graph only at one location. So recall, actually what I could do is, let me redo this so it's more intuitive here. I'll do the axes in white. I'll do the function in yellow. And let's do the vertical line test in red. The vertical line test says, okay, we have a function, a bona fide function, if no matter where I draw a vertical line, no matter where I draw it, it only touches the function at one location. You guys see that? We pass a vertical line across the graph. If it does not intercept the graph in more than one point, it passes it and it is a function. Yes. Yep. That's right, Carrie. Okay. So the vertical line test is what allows you to see whether a graph is a function. So this graph is clearly a function. Okay. What about this graph? Is this graph a function? No, because I can create a vertical line and take a look. It crosses the function at two locations instead of one. So that is not a function. What about this graph? Is this graph a function? Well, let's do the vertical line test. Put a vertical line, put a vertical line, put a vertical line, put a vertical line. We notice that it only touches the function at one location, right? Right? So we may assert that this graph, no matter how jagged or weird it looks, it is indeed a bona fide function. All right. So let's analyze whether this function, this expression is a function. X squared plus y squared is equal to 1. What does this give us? Well, I will tell you right off the bat, that creates a graph for an equation that looks like this. It's a circle of radius 1. X squared plus y squared is equal to 1 is a circle centered at the origin of radius 1. Clearly utilizing the vertical line test as we did before. This is not a function. Let's determine why mathematically, why that is the case. What we'll do is we'll solve for y, because usually our f of x can be expressed as a y. Okay? So let's solve for y in this equation. We first do that by subtracting the x squared. Then we can take the square root of both sides. Then I get y is equal to plus or minus 1 minus x squared. It is precisely the fact that you get plus or minus that causes us to fail the vertical line test. And here's why. The plus generates this picture, the upper half of the circle. And the minus generates this other picture, the lower half of the circle. So if we were to take just plus or just minus, we would actually have a bona fide function because it would pass the vertical line test. But because when we take the square root, we get plus or minus, we generate this, which fails the vertical line test. So if we would want for us to actually get a function out of this thing, we'd either have to take the plus or we'd have to take the minus. We cannot take both. Pretty cool, huh? Isn't that cool? Isn't math cool? Super. That's right. So we were able to review the vertical line test as well. So let's do one last example here of function theory, and we'll move on to 4.1. Let's say I have a table. I have x, and I have f of x, and I see that my inputs are -1, 0, 1, 2, 3. And this function spits out 12, 14, 0, 5, pi. What is f of 3 equal to? Type it in. Yeah, that's correct, Albert. Because x is 3, f of 3 is pi. So what would f of -1 be? That's right, 12. Okay. And what would f of 2 be? 5. I know. It's getting pretty trivial up in here. Okay. So now you guys have everything you need to know for this section. And you know how to graph functions, so you're all right. Let's go back here. Let's go to modules. Bada boom. Bada bing. Time to talk about linear functions. Let me take a sip. 4.1 linear functions. Oh my, linear functions. Oh my, we're gonna have some fun here. This stuff is simple yet complicated. This stuff is simple yet beautiful. Lines, what's more simple than a line? It's just a straight line, you know? How could that be very complicated? It can get complicated. The mathematics can get a little complicated. There's a whole discipline called linear algebra in mathematics, and it's anything but trivial. Really, lines are one of the only ways that us mathematicians know how to do things is to make things linear. It's very powerful because linearity is easy to predict, whereas chaotic behavior is hard to predict. And so if we can, out of the chaos, create order by representing or modeling things with lines, it allows us to actually make powerful predictions. And that's really where the topic of calculus comes to play. But this is not a calculus class. I wish it was, but it's not. So what I'll do is I'll define to you one of the most fundamental concepts of lines. Let's draw some XY coordinates, and let's draw an arbitrary line, okay? And that doesn't even look like a line. That part was kind of bad. That's better, okay? So this is an arbitrary line, Okay, so its equation f of x, the general line equation is mx plus b. Okay, where let's redraw this real quick. Where b right here, this point right here, is the point 0 for x, b for y, called the y-intercept. And that b is called the y-intercept. Y-intercept. Okay, this m here is called the slope. Okay, so what is slope? I'm sure you heard this many times before. Who can tell me what slope is? What you know of it by now? What is slope? Write it there in the chat for me. So it looks like I got nobody paying attention. What is slope? I know you guys can type fast. I know you guys know how to type. So what I've written is it's the change in y divided by the change in x. The intersecting plots. Close. I'm eating at the same time, sorry. I get that, Kiana. I don't remember the definition of slope. That's completely fine, Cody. I'm just glad you guys are corresponding with me. That way I know you're there. Okay, so change in y over change in x. Mathematicians represent change with delta, the Greek letter delta. That represents change, and so delta we put as a triangle. That's the Greek letter for change, okay? So the way we quantify this, let's see how we can talk about this. So let's say this is some point on the line right here, and let's say this is some other point on the line right here. And you know what? This calls for different colors. This is a point on the line. Here's a point on the line, right? Okay. Project this down here. Get that, let's say this is some x1, and we project this down here. Let's say this is some x2. Now, projecting it onto the y-axis will give us different x and y values. This is y1, and this is y2, okay? All right, so change in x really is the difference between these two numbers. And we know the difference between these two numbers can be quantified by taking 2 minus x2 minus x1. Furthermore, the change in these two numbers can be quantified by taking